And archaeologists have long been labouring to shine a light into that forgotten past. They have achieved much. Most scholars now accept that our distant forefathers emerged in Africa to people the globe. Despite mighty barriers of desert, sea and mountain, anatomically modern humans had spread right across Asia and Europe before the last ice age forced them into habitable pockets amid the wastelands. Only after that crisis had passed did our ancestors begin to take up farming, the first step on the way to civilization. Yet trenchant disagreements remain over many of the particulars. Was farming spread into Europe by immigrants or by resident hunter-gatherers taking up agriculture? Why at the dawn of history were people from India to Ireland speaking languages of remarkable similarity? Did migrating Neolithic farmers bring with them the prototype of the Indo-European languages? Or did later Copper and Bronze Age herders do so? Or can we explain this pattern without migration? These issues have been debated for decades. Others have more recently emerged. The spread of farming was traditionally pictured as one long wave inching its way across the continent of Europe from the Near East over thousands of years, whether by the movement of people or ideas. In the 1990s, some archaeologists began to dissent. A new model appeared of farmers leapfrogging their way over previous settlements to create new colonies. Newer still is the idea of farmers arriving in Europe not in one wave, but a complex series of them. Could this be true? The burgeoning field of population genetics offers hope of resolving such wrangles. Within us all we carry evidence of our ancestors. Now that we can read our own code, what stories of our past can it reveal? Ancient population movements can leave a trail in our DNA, pointing to distant relatives we didn't know we had. It was clues from the genes of living people that provided the conclusive evidence, not only that Homo sapiens spread out of Africa, but that the most likely route was across Arabia. When James Watson and Francis Crick described the spiral staircase structure of DNA in 1953, we were a long way from being able to read its code. Their breakthrough was the understanding of how the code worked. Previously, the mechanism of genetics had been a mystery. Gregor Mendel, working in his monastery garden in the 19th century, had worked out some of the basic rules of inheritance by cross-breeding peas. How were the instructions for inheritance passed on from generation to generation? Inside the cells of all living organisms, in the nucleus of each cell, lives the code for making the organism. Its building blocks are just 4 bases. That simplicity makes it so adaptable that it can code for anything from a virus to an elephant. Adenine, A, on one strand of the double spiral of DNA, pairs with thymine, T, on the other. Guanine, G, pairs with cytosine, C. The sequence of these bases is the genetic instruction book. Before it could be decoded, it needed to be transcribed. Geneticists transcribe it into one long chain of letters, such as A, G, 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 T, T, A, C, C, and so on. The human genome has around 3 billion of these base pairs. So mapping the whole human genome was a mammoth task. Working drafts were published in 2001. Another part of our DNA had already been sequenced. Mitochondrial DNA, mtDNA, is not found in the cell nucleus, but in energy-generating mitochondria throughout the rest of the cell. Each mitochondrion is only 0.0005% of the size of the nuclear genome, but there are hundreds or thousands of mitochondria per cell. mtDNA is also different in another way. It is passed down exclusively from mother to child. Picture an unbroken chain of life from the earliest humans through countless generations.